Swayam Prabha. Digital India. Educated India.
Welcome to lecture 32 of the course on econometric methods for statisticians, data scientists and data engineers. The title of this lecture is Identification Problem and Rank Order Conditions. In the last lecture, we discussed the identification problem with the help of a demand supply example. We observed that while estimating a system of simultaneous equations model or a particular equation of the system of simultaneous equations model, often we cannot directly apply the OLS procedure for estimating the parameters of a particular equation. And the reason behind it is that the endogenous variables are also included as explanatory variables in the equation, and since those endogenous variables are usually correlated with the disturbance term, the resulting OLS estimators are inconsistent. So, we require some alternative estimation procedure. Now, we can look at the identification problem from two different angles. First is you can say it is statistician's point of view or the statistician's perspective. For estimating a particular structural equation, since you cannot directly apply the OLS procedure, so one of the option is you go for the reduced form of the equation, apply OLS procedure for estimating the parameters of reduced form coefficients, and then make use of the relationship between the reduced form parameters and the original structural parameters to get the estimators for original structural parameters. Then if that particular equation is unidentified, then you may not get solutions for the original structural parameters. So, you will not be able to estimate the original structural parameters on the basis of estimators of reduced form coefficients. Then another angle from which you can look at the identification problem, it may be termed as say economist's point of view or applied workers point of view. Say if a particular structural equation is unidentified, then it is observationally equivalent to a linear combination of a set of equations in the entire model. Means you consider a particular equation and then you can form a linear combination of another set of linear equations in your model, which is observationally equivalent to this equation. So, you cannot say whether you are estimating this particular equation or a linear combination of that set of observationally equivalent equations. So, these are two different perspectives of looking at the identification problem. One more thing we must notice that the identification problem is not a sampling problem, it is model specification problem. It is not like that we increase the sample size and then we are able to resolve the identification issue. It is actually the model specification problem, and before going for estimating the parameters of a particular equation, we must check the identifiability of that particular equation. Now, in this lecture, we discuss the rank and order conditions for the identifiability of a particular structural equation. We also consider the interpretation of identifiability of a equation in terms of likelihood function. So, now we consider the structural form of the model. We consider this general form of model, say S. We denote this model by S, P y t plus gamma x t equal to u t, and then you have n observations. So, t takes values from 1 to n. Here B is of order m cross m, gamma is of order m cross k, and u t is of order m cross 1. For the y t is of order m cross 1 and x t is of order k cross 1. Y t is the vector of observations on endogenous variables, and x t is the vector of observations on predetermined variables. Then we assume that u t's follow normal distribution, and these are IID also. Then u t's have mean 0 and variance covariance matrix sigma. Then you can easily write the reduced form of the model as y t equal to pi x t plus v t, where pi is equal to minus b inverse gamma. In fact, you can write y t equal to minus b inverse gamma x t plus b inverse u t, and then we write minus b inverse gamma equal to pi and b inverse u t equal to v t. Then v t's are also IID following normal distribution having mean vector 0, and variance covariance matrix of v t is say omega. Now, notice that v t is equal to b inverse u t. So, the variance covariance matrix of v t is b inverse the variance covariance matrix of u t, then b transpose inverse. So, you get omega equal to b inverse sigma b transpose inverse. And then since u t's are IID, obviously for t not equal to L, expectation of u t u L transpose is equal to 0. And then expectation of u t we are taking as 0, expectation u t transpose is sigma. And obviously, expectation of v t is 0, expectation v t transpose is omega, and expectation of v t L transpose is equal to 0 for all t not equal to L. So, v t's are also IID. Now, we can consistently estimate pi using the OLS procedure, because if you look at this equation, in this equation x t's are uncorrelated with v t. So, you can apply the OLS procedure for estimating pi, and the resulting estimator will be a consistent estimator. So, you can consistently estimate the reduced form parameters. Now, if b is known, then you can estimate gamma using the relation gamma equal to minus b pi. So, for given b there is no problem, you can easily estimate gamma. So, the problem comes with the estimation of b, and this makes sense also, because if b is known, you can write b y t equal to z t. So, your model becomes z t equal to minus gamma x t plus u t, and then in this model x t is uncorrelated with u t. So, you can apply the OLS procedure for estimating gamma. So, as long as B is known, there is no problem, we can estimate gamma for given B. So, the problem comes with the estimation of B. Then we must be able to deduce the structural form from the reduced form. So, and if you are able to deduce a unique structural form from the reduced form, then you can estimate B also using the relationship between the structural form parameters and the reduced form coefficients. Now, if more than one structural forms lead to the same reduced form, then we are not sure which structure we are estimating. So, these are two different perspectives from which we can look at the identification problem. Say we must be able to deduce the structural form from the reduced form. The relationship between reduced form parameters and structural form parameters should be such that you get solutions for structural form parameters in terms of the reduced form coefficients. And another angle from which you can look at the identification problem is, if more than one structural forms lead to the same reduced form, then we are not sure which structure we are estimating. Or you can say in this case, those structural forms which are leading to the same reduced form are observationally equivalent. Suppose you have two different structural forms, say S 1 and S 2, leading to the same reduced form, say R. Then we can say that S 1 and S 2 are observationally equivalent. And on the basis of this reduced form, you cannot say whether you are estimating S 1 or you are estimating S 2, or whether S 1 is leading to this reduced form or S 2 is leading to this reduced form. So, in this sense, these two structural forms are observationally equivalent. Now, we consider the identification problem, and then we look at the identification problem using the likelihood function. The joint PDF of y t given x t is, say, p y t given x t, or you can write it equal to p v t. Then p v t is equal to p u t into the Jacobian of the transformation, which is del u t by del v t. Then u t is equal to b v t. So, if we differentiate, then del u t by del v t is equal to b. So, determinant of del u t by del v t is equal to determinant of b, and then we take mod of this. So, this is the Jacobian of the transformation from v t to u t. Then the likelihood function corresponding to S is, say, L equal to p y 1 y 2 y n given x 1 x 2 x n equal to product t equal to 1 to n p y t given x t. And since you are taking product of these n terms, so you get mod of determinant of b to the power n product t equal to 1 to n p u t. So, this is the likelihood function corresponding to model S. Now, suppose we apply a non-singular linear transformation on structural equations 1 with a non-singular matrix D. So, we multiply equation 1 by d. So, we get d b y t plus d gamma x t equal to d u t. So, when we pre-multiply by this matrix D, what we get? We get a linear combination of different equations of b y t plus gamma x t equal to u t. So, we get a linear combination of this. Then we write b star equal to d b and gamma star equal to d gamma. Further, we write u t star equal to d u t. Then we obtain the model, say we denote it by model S star equal to say b star y t plus gamma star x t equal to u t star t equal to 1 to n. So, we have the model S, and then we have taken this linear transformation, we have applied the model S by a non-singular matrix D, then we get the model S star, this one. Then expectation of u t star transpose is equal to d sigma d transpose, because u t star is equal to d u t. So, variance covariance matrix of u t star is, so expectation of u t star transpose is equal to d times expectation of u t transpose d transpose, or d sigma d transpose, and we denote it by sigma star. Say. If we obtain the reduced form for S star, then again we get the same reduced form y t equal to pi x t plus v t, because S star is d b y t plus d gamma x t equal to d u t. So, the reduced form is y t equal to minus d b inverse d gamma x t plus d b inverse d u t. Again, D is a non-singular matrix, B is also a non-singular matrix. So, you get minus B inverse D inverse T x gamma x t plus, then here we get B inverse D inverse D u t. Now, D inverse D is identity matrix, and finally, we get minus B inverse gamma, which is equal to pi, and then here we get B inverse u t, which is equal to v t. So, S star also has the same reduced form y t equal to pi x t plus v t. So, S we denoted by say B gamma sigma, this is the true structure, and S star which is denoted by B star gamma star sigma star is the structure after non-singular transformation. And then both the structures, the true structure S and this structure S star after taking the non-singular transformation have the same reduced form. So, statistically we cannot distinguish them, and both are observationally equivalent. Two different structural forms are leading to the same reduced form. So, if we are using this reduced form, then with this reduced form we are not sure whether we are estimating S or S star, or whether your true structure is S or your true structure is S star. So, in this sense both are observationally equivalent. We are unable to distinguish between these two structures. Further, for the structure S star, we obtain P y t given x t. So, P y t given x t is equal to P u t star, then you have del u t star upon del v t, which is equal to P u t star, and then the Jacobian of this transformation is mod of determinant value of B star. Further, u t star is equal to d u t. So, if we take this transformation, then del u t star upon del u t is equal to d. So, we can write P y t given x t as P y t given x t equal to P u t. Now, we again take the transformation, we take the transformation from u t star to u t. So, we get P u t, then we have the Jacobian of the transformation del u t by del u t star, then you have determinant of B star mod of this. So, we get P u t into determinant of D inverse, and then you have mod of this, then mod of B star is equal to d b. So, you get determinant d b mod of this, and then we solve it, because determinant of d b is equal to determinant of d determinant of b, and then we have taken mod of this, and here you have determinant of D inverse and mod of this. So, this term will cancel out, because determinant of D inverse is equal to determinant of D inverse. So, you get P u t into determinant of B mod of determinant of B here. The likelihood function corresponding to the model S star is, say, L star equal to determinant B star to the power n product t equal to 1 to n P u t star. Now, B star is equal to d b. So, determinant of B star is equal to determinant of D into determinant of B. So, we get determinant of D to the power n, determinant B to the power n, then we also take mod of the determinant product t equal to 1 to n P u t, and then we take the Jacobian of the transformation del u t by del u t star mod of this, which is equal to mod of determinant D to the power n mod of determinant B to the power n product P u t, and the Jacobian of the transformation del u t or del u t star is obtained as determinant of D inverse, and then we take mod of this, and if we take product of determinant of D inverse n times, then we get mod of determinant D inverse to the power n, which will cancel out with this term. So, finally, you obtain mod of determinant B to the power n product P u t, which is same as L, the likelihood function for the model S. So, the likelihood function corresponding to S star is same as the likelihood function corresponding to the model S. So, both the structural forms S and S star have the same likelihood functions. Now, the likelihood function forms the basis of statistical analysis. So, both S and S star have the same implications. For example, if you want to estimate the parameters using the method of maximum likelihood, then both the forms S and S star have the same likelihood function. So, you get the same likelihood estimators. Further, one cannot identify whether the likelihood function corresponds to S and S star. So, in this sense, we are unable to distinguish between these two specifications S and S star. Whether we are estimating S or whether we are estimating S star, we are not sure, or we are not able to distinguish. So, in this sense, S and S star are observationally equivalent structures. Then a parameter is said to be identifiable within the model if the parameter has the same value of all equivalent structures contained in the model. So, if the parameter has the same value for all equivalent structures, then it is identifiable, otherwise not. Further, a particular structural equation is identifiable if all the parameters in the structural equation are identifiable. Then a given structure, we can find many observationally equivalent structures by a non-singular linear transformation. You can take different matrices like D, different non-singular matrices like D, and then you get a non-singular linear transformation. So, you can find many observationally equivalent structures. Then the presence and or absence of certain variables help in the identifiability. If certain variables are present or absent in a particular equation, then it helps you. So, you require some priority restrictions on B and gamma, and these priority restrictions may help in identification of parameters. Some of the prior restrictions like say some of the coefficients are equal to 0, and these priority restrictions may arise from various sources like economic theory. So, on the basis of your economic theory or your economic hypothesis, you get such kind of priority restrictions, and such kind of priority restrictions help you in the identification of parameters. Then for the identification of an equation, some of the variables must be excluded from the equation which are present elsewhere in the model, and this is known as exclusion of variables criterion or zero restriction criterion. So, some of the variables which are present elsewhere are absent in that particular equation, and these restrictions are exclusion restrictions or exclusion criterion or zero restriction criterion. Now, we consider the order conditions for identification. A necessary condition for an equation to be identified is that it must exclude at least m minus 1 endogenous and predetermined variables. So, a particular equation is identifiable if it excludes at least m minus 1 endogenous and predetermined variables. M is the total number of endogenous variables present in the system, and notice that this condition is just necessary condition. If it excludes exactly m minus 1 variables, then the equation is just identified. And if it excludes more than m minus 1 variables, then it is over identified. Equivalently, for an equation to be identified, the number of predetermined variables excluded from the equation must not be less than the number of endogenous variables included in the equation less 1. Just to show the equivalence between these two conditions. Suppose small k is the number of predetermined variables included in the equation, and small m is the number of endogenous variables included in that equation. Then total number of predetermined variables is k, and in that particular equation you are including small k number of predetermined variables. So, total number of excluded predetermined variables is k minus small. This is the total number of excluded predetermined variables. Further, small m is the number of endogenous variables included in that equation. So, the number of excluded endogenous variables is capital M minus small m. So, the total number of excluded variables is k minus small k plus capital M minus small m. And for identifiability, the total number of excluded variables must be greater than or equal to m minus 1. We must exclude at least m minus 1 endogenous and predetermined variables. It means k minus small k plus m minus small m is greater than or equal to m minus 1, or equivalently capital K minus small k is greater than or equal to small m minus 1. So, the number of predetermined variables excluded from the equation, this is the number of predetermined variables excluded from the equation, must be greater than or equal to the number of endogenous variables included in that equation less 1, means small m minus 1. If capital K minus small k is equal to m minus 1, then the equation is just identified, and if capital K minus small k is greater than m minus 1, then the equation is over identified. So, suppose we consider this example of demand function and supply function. The total number of endogenous variables is capital M equal to 2, and the total number of predetermined variables is capital K equal to 1. You have just one predetermined variable. The endogenous variables are Q and P. These are the endogenous variables, and predetermined variable is your interceptor. So, capital K is equal to 1. So, capital M minus 1 is equal to 1. Each of these equations must exclude one variable for identification, but this does not hold for any of these two equations. All the variables are included in the first equation, all the variables are included in the second equation. No endogenous or predetermined variable is excluded from the first or second equation. So, none of these equations is identified. Both demand function and supply function are unidentified. Then we take another example. Your demand function is Qt equal to alpha naught plus alpha 1 Pt plus alpha 2 It plus u1 t. Supply function is Qt equal to beta naught plus beta 1 Pt plus u2 t. So, in the demand function we have incorporated one more variable It, which is exogenous variable. Then capital M equal to 2, capital K equal to 2. One intercept term you have, and then you have this exogenous variable. Now, the supply function is just identified as it excludes m minus 1 equal to 1 variable. If you look at the supply function, it excludes It, but the demand function is unidentified. Now, we consider this example. In this example, we have incorporated one more predetermined variable in the equation, that is Pt minus 1, one lagged value of Pt. So, here capital M is equal to 2 and K is equal to 3. You have in all 3 predetermined variables. You have 2 exogenous variables, the intercept term and It, and one lagged endogenous variable. So, you have 3 predetermined variables. Further, each of these equations excludes exactly m minus 1 equal to 1 variable. Demand function excludes Pt minus 1. So, the demand function is identified. Supply function excludes It. So, supply function is also identified, and both the equations are just identified. Now, we consider this example. Here we have the predetermined variables. One means the intercept term, It, Rt and Pt minus 1, and of course, the endogenous variables are Q and Qt and Pt. The total number of endogenous variables is 2, and total number of predetermined variables is capital K equal to 4. And capital M minus 1 is equal to 1, then the demand function excludes one variable, which is Pt minus 1. So, it is just identified. The supply function excludes 2 variables, It and Rt, which is greater than 1. So, the supply function is over identified. Now, we consider the rank condition of identifiability. The order condition is necessary, but it is not sufficient condition for the identification of an equation. The rank condition provides you a sufficient condition for the identification of an equation. To check the rank condition, in a simultaneous equation model containing capital M equations in m endogenous variables, an equation is identified if and only if there exists at least one non-zero determinant of order capital M minus 1 from the coefficients of endogenous and predetermined variables excluded from that particular equation, but included in the other equations of the model. So, this is the rank condition. Then notice that the rank condition states whether the equation is identified or not. So, it is a sufficient condition to check the identifiability. From the order condition, we know whether the equation is just or over identified. So, suppose first you check the order condition. If the equation is unidentified, then there is no need of going for the rank condition. If the equation is identified, Then the order condition also tells you whether the equation is just identified or over identified, but it is just a necessary condition. So, you further verify the identifiability using the rank condition. Say, suppose we consider this particular model and we check the identifiability of each and every equation of this model. Here y's denote the endogenous variables and x's denote the exogenous or predetermined variables. So, obviously, capital M is equal to 4, you have 4 equations and 4 endogenous variables also. Capital K is equal to 4, you have one intercept term, then x1t, you have x2t, you have x3t. So, in all you have 4 exogenous variables, capital K is equal to 4. So, first we check the order condition. Now, capital M minus 1 is equal to 3. Now, you can easily verify that from the first equation, say x2t is excluded, x3t is excluded and y4t is excluded. So, in all 3 variables are excluded. So, order condition is satisfied. From the second equation, y1 is excluded, y4 is excluded, then x3 is excluded. Again 3 variables are excluded from the second equation. So, using the order condition, it is identified. From the third equation also, say it has y1, it does not have y2, so y2 is excluded, it does not have y4, so y4 is excluded, then it does not include x3. So, again it excludes 3 variables. So, again using order condition, it is just identified. Similarly, for the fourth equation also you can check, the fourth equation is also just identified using the order condition. Now, we check the rank condition. To check the rank condition, we write the system in the tabular form. So, you have 4 equations and one is corresponding to the intercept term, then you have y1, y2, y3, y4, x1, x2, x3. Now, in the first equation, the coefficient of intercept term is minus beta 1 0. If you look at the first equation, the intercept term is minus beta 1 0. The coefficient of y1 is 1. The coefficient corresponding to y2 is minus beta 1 2. Then corresponding to y3 you have minus beta 1 3. Then y4 is excluded from the first equation. So, you write 0 here, corresponding coefficient is 0. x1 has coefficient minus gamma 1 1. x2 is excluded from the first equation. So, you write the corresponding coefficient as 0 here, and then x3 is also excluded. So, you write 0 here. Similarly, you can write the coefficients corresponding to second equation, third equation and fourth equation also. Now, we strike out the columns corresponding to non-zero coefficients of the first equation. Now, suppose you check the identifiability of the first equation. Then we strike out the coefficients corresponding to the non-zero or the columns corresponding to non-zero coefficients of the first equation. and then we also strike out the first row or the row in which the first equation appears. So, ultimately we get these coefficients. We write these coefficients in the form of this matrix. So, you get this matrix using the remaining entries. Then by rank condition, the first equation is identified if there exists a determinant of order m minus 1 equal to 3 formed from the entries of A, but can you form a determinant of order 3 from the entries of A? No, it is not possible. Why? Because the only determinant is of order 3 which can be formed from the entries of A is the determinant value of A itself, and the determinant value of A is equal to 0. You can easily verify it. So, no non-zero determinant of order 3 exists. So, the equation is unidentified. Remember that when we check the order condition, the order condition leads to the conclusion that the first equation is identified, just identified. But if we check the rank condition, then by the rank condition the first equation is unidentified. Similarly, we can check the identifiability of the second equation also. Again, corresponding to second equation, we strike out the columns corresponding to the non-zero elements of the second equation, and then we strike out the row corresponding to the second equation. So, ultimately we get this matrix. We get the matrix A with elements 1 minus beta 3 1 minus beta 4 1, 0 0 1, 0 0 minus gamma 4 3. Again, if you look at the determinant value of A, the determinant value of A is 0. So, you cannot form a determinant of order 3 which is non-zero. So, no non-zero determinant of order 3 exists, and the equation 2 is also under-identified or unidentified. Again, notice that using the order condition, the second equation was just identified. But when we check the rank condition also, then we get the conclusion that the equation is under-identified or unidentified. Similarly, for the third equation, we strike out the columns corresponding to the non-zero coefficients of equation 3, and then we strike out the row corresponding to the third equation, and ultimately we get this matrix. Again, if you look at the determinant value of A, then the determinant value of A is equal to 0, and you want a non-zero determinant of order m minus 1 equal to 3 formed by the elements of A, but you cannot form a determinant of order 3 which is non-zero using A. The only determinant of order 3 is actually the determinant value of A itself, and this is 0. So, this equation is also unidentified. you can easily verify that the equation 4 is identified. So, to check the identifiability of fourth equation, you look at the matrix, say you delete this column, this column, this column, the columns corresponding to the non-zero elements of equation 4, and then you delete the row corresponding to the fourth equation, and then you get this matrix. You find the determinant value of this matrix, say determinant value of minus beta 1 3, minus beta 2 3 1, then you have minus gamma 1 1, minus gamma 2 1, minus gamma 3 1, 0, gamma 2 2, minus gamma 3 2, and the determinant value of this matrix is non-zero. So, equation 4 is identified, and according to order condition, the equation 4 is just identified. So, using rank and order condition, we lead to the conclusion that the equation 4 is just identified, but equations 1, 2 and 3 are unidentified. We consider this example also. Here again y's are endogenous variables and x's are exogenous variables. Again capital M equal to 2, capital K is equal to 3. For the first equation, small m is equal to 2, it has 2 endogenous variables, small k is equal to 1. Capital K minus small k is equal to 2, m minus 1 is equal to 1. So, the first equation is over identified according to the order condition. In the second equation, small m is again 2, you have both the endogenous variables here, small k is equal to 2. So, k minus k is equal to 1, m minus 1 is 1. So, equation 2 is just identified according to the order condition. Then you can check the rank conditions also. Say according to check the rank condition, we write the coefficients in this form. Say you take first equation, second equation, then you take y1 t, y2 t, x1 t, x2 t, x3 t here. Then corresponding to the first equation, you delete this column, this column, this column, and then you delete this row also. So, you get this matrix. We can form a non-zero determinant from A of order m minus 1 equal to 1. So, you can take say determinant gamma 2 2 or determinant gamma 2 3. So, the first equation is over identified, means according to the order condition it is over identified, and then it is identified according to the rank condition. Similarly, for the second equation, A is equal to gamma 1 1, and then equation 2 is also identified, and it is just identified because according to the order condition it is just identified. So, in this lecture we have looked at the problem of identification from the angle of likelihood function, and then we have also discussed the rank and order conditions for the identifiability of a model. We observed that the order condition is a necessary condition, but a sufficient condition for the identifiability is provided by the rank condition. In different examples, we have observed that there are cases in which the order condition shows that the equation is identified, but when we check the rank condition, we get the conclusion that the equation is actually unidentified. So, before going for the estimation, we must check both the conditions, order condition. If on the basis of order condition some equation is unidentified, then you do not have to go for the rank condition. But if on the basis of order condition some equation is just identified or over identified, then we must check the rank condition also, and then on the basis of rank condition only we can say that the equation is identified. In this lecture I have not given you the derivation of the rank or order conditions. In the next lecture we will discuss the detailed derivation of rank and order condition for the identification of the equation. So, I am going to stop here. Thank you.
Hello, I am Shikha Dikshit. I teach psychology and I am with the Department of Humanities and Social Sciences at IIT Kanpur. Today I am going to talk about what is social cognition. Social cognition is a research area in psychology which explicates the various cognitive processes that people employ to understand the social world. So, essentially it is about sense making of the social world, which involves understanding other people as well as understanding oneself. Understanding others requires understanding their traits, their internal tendencies, their contextual aspects, motives, feelings, emotions, etc. So, as we can see, this is a very complex process and requires a massive amount of information processing. Even for small decisions, for simple decisions, people have to process a large amount of information. The main perspective or the approach which is used in social cognition is obviously the cognitive approach, and which is the study of mental structures and processes. The main paradigm which is used is the information processing paradigm. As far as the range of topics in social cognition is concerned, the range is very wide, from individual level sense making to collective sense making. As far as views of cognitive sense making are concerned, there are three major dominant views in social cognition: the naive scientist view, the cognitive miser view, and the motivated tactician view. The naive scientist view emerged from research done in causal attribution, and this refers to detailed and systematic processing of information and sense making in the social world. However, it is not always possible to make detailed engage in detailed cognitive processing, and hence people act as cognitive misers in many situations. So, whenever there is lack of time and cognitive effort is less, then people involve in using certain strategies which are functional, yet they are like mental shortcuts. So, this is the cognitive miser approach. However, the question that comes to the fore is that which one of the two strategies is more important? The answer is provided by the motivated tactician view. And according to this view, people can either use the naive scientist approach or the cognitive miser approach as and when required, and they can switch over between the two approaches when required. So, these are the three major views which are utilized to understand cognitive sense making. The topics that social cognition covers ranges from cognitive social cognition to social cognition. So, topics such as causal attribution, understanding of attitudes, social schemas, unconscious cognition about social situations, the use of mental shortcuts or heuristics in decision making, social identity and stereotyping processes are some of the topics. In addition to this, a large number of social cognitive psychologists also understand collective sense making in terms of social representations.